Let's do one more example. So let's work with this function, the absolute value of x minus 1, and show that it's differentiable everywhere except at x equals 1. Okay, as a general rule of thumb, whenever you see an absolute value, there is going to be a problem of differentiability whenever what is inside, in this case x minus 1, becomes 0. Okay, so we should expect that this absolute value of x minus 1 has a problem of differentiability, a corner at x equal 1. Let's see that more precisely. So this function, let me write it. First thing we need to do is to write carefully what the absolute value function means. So this function is x minus 1, whatever is inside, if x minus 1 is positive, and it's the negative of what is inside, in this case 1 minus x, if x minus 1 is negative. Okay, but we don't write it like this. We write x bigger or equal than 1 and x less than 1. Okay, so this is the function f of x. Now it's defined piecewise. Okay, we can plot it. Let's plot it here. So we have the function x minus 1 that crosses here. Okay, and then we have the function 1 minus x that goes like this. Okay, and we have here the function f of x. Let's use, here we go. Did you notice there is a corner at x equals 1? So this is my function f of x. Okay, so from the graph, clearly there is a problem of differentiability at x equals 1. And everywhere else, differentiability has to do with the slope. Everywhere else, the slope is constant. So it's going from the picture, okay, from the plot. So it's going to be differentiable everywhere else. But let's show it using the definition. So the definition says that we need to check the differentiability, that the limit as x tends to a of f of x minus f of a divided by x minus a, okay? So this limit exists, all right? Then f is differentiable at x equals a, okay? So let's do this. They ask to check everywhere, so let's start with values of a that are smaller than 1, okay? Then we do bigger than 1, and then we do 1. So let's say a is less than 1, whatever number. If you don't like to use a letter, a parameter, a, you can just do it for 1/2 and then do it in general for a. Okay, but in this case, the limit is as x tends to a, f of x minus f of a divided by x minus a. These problems are always the same. Now we write down what is f of x. Okay. So because x tends to a will be a number here and a number less than 1. Okay, and we are interested in the limit. We can take values that are very close to a. Okay, those values that are very close to a, we can assume that they are already on the left of 1. Okay, that they are smaller than 1, because that's the limit process. You only care about the values, infinitely many values that are infinitely close to the number a. Okay, so we have here the limit as x tends to a of 1 minus x minus 1 minus a. Okay, divided by x minus a. So this is, these two ones cancel out, and we have minus x plus a. Well, this would be the limit as x tends to a of negative x plus a divided by x minus a, and this is negative 1. Okay. All right. So we see that the slope, the derivative is negative 1. The slope is negative 1. And if you notice, when we look at the function 1 minus x, we can tell what is the slope. The slope in this case, because it's linear, we know it's negative 1. So because the derivative is the slope, we see that everything matches together. All the information is coherent. Okay, so because this limit exists, f is differentiable. Okay, now a bigger than 1, so it's the same definition, so I'm just going to copy paste. Okay, the limit as x tends to a of f of x minus f of a divided by x minus a. And now it's the opposite process. Okay, so now we have our value a that is bigger than 1. Okay, and now as we take the limit, we are only interested in values that are very close to a. Okay, because that's the limit process. Okay, so this would be the limit as x tends to a. What is f of x? In this case, it's given by x minus 1 because x is bigger or equal than 1. In this case, bigger actually. So this is x minus 1 minus a minus 1 because a is bigger than 1 divided by x minus a. And again, the ones cancel out. And I get x minus a divided by x minus a. So the limit is 1. So then f is differentiable at a bigger than 1. Again, if you notice, because the function is x minus 1, the slope is clear, right? It is 1 because it's the number that goes with the x. It's a linear function. Precisely what we got here. So there is one more value that we need to check. A equal 1, but this one is the one that is going to be problematic. So let's check if the limit works. So to see if the limit works, we need to take the lateral limits, right? If both of them are equal, then we can say that the limit exists. Okay, notice here, because a equals 1, in place of a, I'm always writing 1. Okay, so this is limit x to 1 from the left. From the left means the numbers that are less than 1. So if the numbers are less than 1, the function is 1 minus x. All right, so this is 1 minus x minus 1 minus a divided by x minus 1. The ones cancel out. Sorry, I wrote silly me. So because a is 1, what I get here is the limit from the left is 1 minus x divided by x minus 1, and this is negative 1. Okay, so here the problem is that a is equal to 1. I was writing a, okay, but there is no need. A equals 1. Okay, so this is negative 1. And then let me check the limit from the other side. Did you notice what happened here? No, so we are approaching from the left. The slope is negative, it's minus 1. Okay, Now, as we approach from the right, we should get the slope equal to 1. And that's going to be the problem. There's going to be a mismatch. Okay, so from the right, f of x minus f of 1 divided by x minus 1. So this is now, because we are approaching from the right, and on the right is defined as x minus 1. So this is x minus 1 minus 1 minus 1 divided by x minus 1. Okay. Is to cancel out, and this is equal to 1. Okay, so you see we got 1, we got negative 1 before. These two are different, so the limit does not exist. Okay, this is because the lateral limits don't coincide. Okay, and if the limit does not exist, then the derivative does not exist. This is at x equals 1.